Volcanoes are arguably one of the most extreme forces to be reckoned with on the face of the planet. The heat and the lava that dissipates from the Earth's core is hot enough to melt entire villages. It can be catastrophic to the human race. But volcanoes do not care. They do not discriminate who will be consumed in their path. But at the same time, they're also responsible for much of our existence. They have a role in the water we drink, in the fossil fuels we consume, and the metals we incorporate into our technology. I have Dr. Clive Oppenheimer with me today, a distinguished volcanologist at the University of Cambridge, who has traveled to some of the most remote places in pursuit of measuring and analyzing these volcanoes. He has conducted extensive research in Antarctica on Mount Erebus, one of only a handful of active lava lakes. He has gone to North Korea, which for anyone in the US, they know that's a particularly rare feat, to assist with research about the Paektu Sun volcano. I might be pronouncing that incorrectly. He is also the author of a fascinating and exceptionally well-written book, Mountains of Fire, The Menace, Meaning, and Magic of Volcanoes. And he's here to discuss all of that and more. So, Dr. Oppenheimer, thank you so much for coming on. Really appreciate your time today.
My pleasure. Thank you for the invitation.
Of course. So let's just start from the basics here. Why are volcanoes important in the Earth's in general and even beyond? Because they can exist on other planets as well, right?
That's right. Volcanism is a planetary process. We see it on other planets and moons in the solar system. And for sure, there are volcanoes on exoplanets in other solar systems. And so, I mean, it's part and parcel, I think, of what it is to be a planetary body, which has got heat inside. And a volcano is really an aperture in the surface of a planet or moon through which heat and rock, molten rock, or even other kinds of fluids. Maybe we could consider geese as a kind of volcano. This is quite commonplace around the solar system, and they are responsible for supplying the atmosphere. The lighter elements within a planetary body are spewed out of volcanoes and form on our own Earth, our own planet. They form the oceans and the atmosphere and the ice sheets.
And so in terms of the environmental record of the Earth or any planet really, how do you go about, how would you go about analyzing a volcano? Because you could do it through gases, you could do it through the rock. So what's typically the process for that as a science, from a science perspective?
There are a number of ways that you can approach it. I mean, you mentioned one, the rocks. That's the traditional way, is to go out with a geological hammer out to the mountain and bash off a few chunks of rock and take them back to the lab and analyze them. And those rocks, of course, are the products of eruptions, and they'll really reveal clues about the kinds of eruptions that produced them and how deep down was the molten rock that fueled a volcanic eruption of the past. But there are many other ways, as you say, as well. We can monitor volcanoes. We can put like a stethoscope on them in the form of seismometers, or listening through the gas emissions, measuring those and using them as messengers of the processes going on deep within the Earth. And there are other techniques looking at the changing shape of the ground surface that might respond to the ascent of molten rock towards the surface that will cause a volcano to bulge out. Those are all things that we can detect and interpret. But then there are completely different ways of studying volcanoes that might mean you never even go to a volcano. You study it in a model, in a numerical computational model, or I even have colleagues who build analog volcanoes in the laboratory using syrup and different kinds of fluid and adding bubbles and particles and trying to understand the fluid mechanics of magmatic and volcanic processes.
That's cool. So when you're going about the modeling side, right, whether it's a mathematical model or an analog model, as you said, is the purpose mostly for to warn people, or is it to understand the underlying structure of the volcano or the underlying dynamical system that is going on within the Earth, or what is kind of the ultimate research aim? Or it might not necessarily be one. There might be multiple goals or secondary effects, I suppose.
I think if I had to distill, a fundamental aim, it's really to visualize what it looks like down there underneath a volcano. It's a region that we can't access directly, and so an awful lot of volcanology is about trying to image in some way to be able to visualize where are the roots of a volcano, how deep down is the magma, what's it up to, what kind of magma is it, what kind of temperature, and is it going to erupt or not? So, I mean, that's I guess, a fundamental question. And then you could maybe say there are two kinds of volcanologists. There are volcanologists like myself that are based in universities that are doing more fundamental research, trying to understand how volcanoes work, why they erupt when they do, why they stop erupting when they do, why they have particular kinds of eruptions. And then there are volcanologists in institutes, particularly volcano observatories like the US Geological Survey observatories in Hawaii or the Cascades, and also in meteorological offices, there are volcanologists. And they have that operational role, which is more about monitoring and being able to interpret real-time data in terms of what a volcano might be up to. And that, of course, feeds into civil protection and hazard assessment.
Sure. So you've had quite a distinguished career so far. What kind of got you into this field? Like, was it something that you've always been interested in as a kid, and just we all know Krakatoa and like read about it in the comic books and everything, but was it always a lifelong passion, or is it something that you kind of found you had to weave your way through your studies and eventually found interest in?
Yeah, no, I did see that movie Krakatoa East of Java when I was a kid. It was on TV, but I think it goes back even a little bit earlier than that. Maybe when I was around 10, visiting the Geological Museum in London, the city where I grew up in the UK, and I just loved the aesthetics of these wonderful minerals, rocks, fossils, and that I think is what seeded a passion for geology, which I studied at university, and I particularly appreciated the geology that's happening now. So in fact, I thought I might go into seismology for PhD studies. But I'd traveled in Indonesia before going up to university. I'd seen a lot of volcanoes. I traveled with a book by a guy called Peter Francis, called Volcanoes, and I'm looking in this book and recognizing some of the features that I'm seeing right in front of my eyes. And I didn't know then that Peter Francis would end up being my PhD, my graduate advisor a few years later. And so I went into volcanology at that point, and it was a PhD looking at how to monitor volcanoes from space. And so those were two topics that were new to me. Volcanology, I knew very little about. Remote sensing, imaging from Earth's orbit, and particularly I was trying to measure temperatures of volcanoes for using satellite data. That was also new to me. And that's what really propelled me then into a career in volcanology.
Sure. Yeah, remote sensing is a really interesting area because it has a wide range of applications, and I guess it's not necessarily satellites, right? I mean, that's the predominant source of remote sensing data, I guess. But you actually made a documentary with Werner Herzog called "Into the Inferno," and there's a part of the documentary where this woman has this device that essentially is bouncing. I guess it's a laser or some kind of light source, and seeing how quickly it reflects back off the volcano, and you can pretty much use that to figure out if the bulge of the volcano is expanding or not, right? That would also be considered remote sensing, or not really.
Yes, I think, I mean, a very broad definition of remote sensing would be gathering information about an object without being in direct contact with it. So, sticking a thermometer in my mouth to measure my temperature, that wouldn't be remote sensing. But having a device maybe to record someone's temperature from their forehead from a little distance, that's a kind of remote sensing. And the technique that you referred to is electronic distance measurement, and it's fairly standard surveying kit that you'll see sometimes people in engineers on the road surveying will have a similar system, a little telescope, and it's firing off a laser pulse, and there's a mirror, and the travel time of the pulses of light are being measured, and that gives the range, the distance between the mirror and the instrument. And the same technique is used on volcanoes. You can put a little corner cube that will reflect the light, position it in a fixed spot on the volcano up towards the summit, and ping it with a laser light once a day, once a week as needed, and measure that distance. And if that distance gets shorter over time, then it means, well, it either means that you're moving nearer the volcano, or more likely the volcano is moving a bit nearer you by bulging out because molten rock is moving up towards the surface.
That's hilarious. I see those people on the side during construction, and I always wonder what they're doing. So now I know. But yeah, it was a really interesting part of the documentary. And I'm happy you explained that, because I think you also have some patented device that works similarly. Yeah, maybe explain that device, because I'm not entirely sure how that differs from the remote sensing that you were just describing.
After my PhD, which was using satellites looking down at the Earth, I actually got more involved in using ground-based instruments, still remote sensing instruments, to measure volcanic gas emissions. And the device you're referring to is an ultraviolet spectrometer. So these were very compact, relatively cheap devices that were being mass-produced. And the ultraviolet light is everywhere in the daytime sky. It's the light from the sun that's scattered by the air molecules. And there's one particular gas that streams out of volcanoes, sulfur dioxide. It's an acidic gas. It'll tear your eyes up. It's not particularly pleasant to breathe. And it's an important gas to measure. It's again telling us about the activity of a volcano. And once it's emitted into the atmosphere, it drifts with the wind. And sulfur dioxide absorbs certain wavelengths of ultraviolet light. And so we would hook up one of these little spectrometers to a telescope, point it up at the sky, and typically drive backwards and forwards on the roads, maybe a few miles downwind of the volcano summit. And we would be able to measure all of the sulfur dioxide coming out of the volcano and convert that into how many tons per day of this gas were coming out of the volcano. And it's another measurement. If you measure, repeat that over time, you do it daily, weekly, monthly, again, depending on the activity of your volcano, you build up a time series and you can see, are there trends? Is it increasing? Is it decreasing? And that's a very important diagnostic of what a volcano is up to.
And so I guess on that note, the time series of data that you would be looking at would be for like the immediate future to see if something's going to happen, right? Like, I guess in the relative time span of the volcano, I mean, that's a dot on the map, right? So like that kind of information would be used for more like prognostic, like, what do we expect to happen for the safety of the people, I guess. Is that the idea?
Yes. So again, because I'm based in a university, I don't have that 24/7 operational responsibility, but I've worked very closely with colleagues who do, and we've designed approaches to making these measurements that are now quite mainstream around the world in different volcano observatories in Hawaii, for example. And so there, yes, you're collecting data, and when I've visited observatories, there might be a weekly meeting where everyone measuring in different ways gathers together and says, this is what the seismology is showing. This is what the geodesy, measuring these changing shape of the ground. This is what that signals are being measured. Here are the gas measurements. And what do we think this means? And maybe then you also evaluate what might happen over the next week, over the next month, over the next 6 months. My kind of work tends to be more what I would call campaign measurements. I've worked on active volcanoes where I can make very detailed observations of the gas emissions in particular, but also thermal imaging, and look at very dynamic changing volcanic behavior, for example, at lava lakes, and get these very, very detailed data. And there I'm really trying to understand more how is this volcano working at a more fundamental level. So I'm not trying to forecast the activity, but really to understand the process.
Okay, more of the inference rather than the prediction, I suppose. Speaking of lava lakes, you mentioned that the device was used to capture. You said it was sulfur dioxide.
That's right.
So in Mount Erebus, the main gas that was emitted was nitrogen dioxide, I believe. Right? Is that
No, actually, so nitrogen dioxide is an interesting one. It doesn't really come directly from volcanoes, but because volcanoes are very, very hot sometimes with lava at the surface, they can fix atmospheric nitrogen, which is the most abundant molecule in in air. They can basically cook it and turn it into nitrogen oxides. So we have measured that spectroscopically at volcanoes, but it's the air nitrogen that's being oxidized. The most abundant gases that come out of Mount Erebus in Antarctica are water and carbon dioxide, and that's true of pretty much any volcano on the planet. The main two gas emissions are water and CO2.
yeah? And I think that's something that a lot of people don't realize. It's like I guess humans wouldn't really be here if it wasn't for volcanoes because they are directly responsible for the water we drink in many ways, right?
Yeah, we've got about the same composition actually. If you work down, the elemental proportions of the human body and the gases that come out of volcanoes, they're very, very similar, surprisingly similar. We've got a bit more nitrogen, maybe a bit more phosphorus, and the volcano's got a little bit more sulfur. But yeah, I mean, we're made up of the chemicals that have been emitted from volcanoes over the eons. They've been fixed by plants and so on. But we're part of this great geochemical cycle that sees elements coming out of volcanoes, being part of the carbon cycle, being part of ecosystems, and then ultimately uh, those chemicals go back into the inner earth at the edge of places like the Pacific tectonic plate, where the Earth's crust is sinking back into the deep interior, and it's returning some of those elements back to the inner Earth, and they'll come out again eons later out of volcanoes.
Cool. So one more, I guess, science question before we kind of move to more of the adventure aspect of what you do. But I have obviously a very cursory understanding, but the way that when volcanoes erupt, the lava flows harden, and that's eventually how you get these like rock layers, as we kind of touched on in the beginning. I know most of your research has to do with the gases and the not rock aspects. But maybe just for anyone who's wondering, just so they kind of have a comprehensive understanding, like how would you go about analyzing, like, I don't know if it's sedimentary rock or whatever the layers may be, if you were to drill and you could essentially find a time series of the Earth's history as well using those layers of molten rock. I might be butchering the vocabulary, but pretty much like as it hardens and then erupts again, it hardens again, you create all these layers, and that's kind of how you can determine a record of the Earth's history, right? Something to that extent.
Yeah, no, absolutely. Yeah, the I guess the most basic principle of geology is that the rocks that form at the Earth's surface, whether that's sediments in the oceans or whether it's ash and lava from a volcano, that they kind of stack up over time. And so, as you say, if you slice through that or drill through it, then you see revealed what we call the stratigraphy, the layers that go back in time. That can get turned upside down, of course, by earthquakes and tectonic activity, but that's a sort of a basic principle for us.
And then the term fossil fuels is because of the fossils that are buried in those rock layers, right? That's like the idea. Like once they fossilize, those gases escape into the rocks, but they don't escape into the surface. That's why you can drill down and obtain it. Am I sort of correct on that, or?
So fossil fuels are the product of biology from geological eons ago, organic matter that decayed, that was buried by sediments, and so this is why many hydrocarbons are recovered by drilling beneath the sea, drilling into the rock to reach a level where they've accumulated, and basically they've this organic residue is a fossil. It's fossil material that has rotted, decayed, and matured, usually because of some heat deeper down in the Earth's crust, and it makes oil, it makes gas, and if that can get trapped geologically by a less permeable layer of rock, that's what makes an oil or gas reservoir that can be tapped by drilling down. So that's why they're called fossil fuels, because basically it's the remains of things that were living millions of years ago.
Sure. Okay. Great. Now, shifting gears a little bit to the adventure itself of being a researcher as a volcanologist, one of the coolest things, in my opinion, is that you get to go to like literally some of the most remote places on Earth. I have this fascination with Antarctica. I think it's such a wild place. It's the only place on Earth that's not owned by anyone. It's all kind of communally agreed that it's like a place for research, and like we're not there to destroy it and all that. So you did a lot of work on Mount Erebus with regard to the lava lake that's contained within there. So maybe just give a little bit about like why you decided to go down to Antarctica, what specifically about Mount Erebus is appealing from a research standpoint, and like what was that experience of like going there for the first time?
I first heard about Erebus on day one of my PhD studies many years ago at the Open University in England. There was a pile of computer tapes on my desk and a note from my advisor saying, these are from a volcano called Erebus. It's in Antarctica. Take a look at them. They're thermal infrared images, and see if you can, see the lava lake that this volcano has. And so that was my sort of gateway drug, if you like, to getting down to the ice down near the South Pole. In these images, the pixels were 1 kilometer by 1 kilometer, so nearly a mile squared on the ground. So you couldn't make out a lot of detail. But sure enough, this lava lake would light up one of the pixels because it was so intense. So I knew about Erebus, and some years later, I met a geochemist called Phil Kyle, based at New Mexico Tech, and he said, "Oh, I've been working on Erebus for many years now. You should come down with us sometime." And so I was extremely excited at that prospect, but it was quite a few more years before he got in touch and said, I think we can get you on the team this year. And it was because he'd read about the work that we'd done with these little tiny ultraviolet spectrometers. He'd been doing the same kind of measurements, but with some really hefty, pretty antiquated equipment. And so he was excited by what we were able to do with these very, very cheap instruments. And so I went down there, and what was it like? I mean, so this was with the US Antarctic program. We'd fly into Christchurch, New Zealand. That's the jumping off point to McMurdo Station, a US base in Antarctica on Ross Island, due south of New Zealand. The largest scientific base in Antarctica, about 1,000 people in summer. So you show up, and it's already pretty amazing, but you're at sea level. There's lots and lots of people there. There's a big galley. There's cargo moving all around. There's scientists, and it doesn't prepare you for the real Antarctica, which you experience the second you step out of the helicopter up on the flanks of the volcano. So now we're going up 10,000 feet, and now you really experience the cold. Well, we're getting to the point where Celsius, which I use, and Fahrenheit converge at -40. I discovered that working in Antarctica. So we're approaching those kinds of temperatures, and the air is incredibly dry. and you've got all this gear on, you know, gear to keep you warm, and you step out of the helicopter and you feel a bit like you've stepped out onto the surface of Mars, maybe. It's so alien, the environment and the landscapes and skyscapes are just phenomenal at that altitude. You look out across the Ross Sea, which has these icebergs breaking up and floating around in the distance. So the Transantarctic Mountains that themselves go up 12, 13,000 feet, and you see glaciers streaming off them and the light gleaming off those. So it's really very, very spectacular. And we would then spend about a month in a small field camp, maybe 10 of us, just a mile and a half from the summit crater of Erebus, 12,500 meters up, sorry, 12,500 feet up. And we would, we had a very comfortable accommodation there. We had a couple of huts so we could cook, eat, hang out. We had a workshop where we could fix everything that was broken on the journey up there, and sit out the bad weather. And when we had good weather, 24-hour daylight this time of year, November, December, and so you can just work and work and work. And on a windless day, just beautiful, sunshine, and you don't even feel too cold. If the wind is down, and I'd be up at the edge of the crater maybe for several hours, setting equipment up, making observations, collecting these data. So yeah, it was the time of my life, absolutely, on up on that mountain.
That's fantastic. What was the sensation like going from this extreme cold to this extreme hot of being like right at the crater's surface or edge, I guess? Was that like, did you have to, I'm assuming you had to take some stuff off or you would overheat maybe, or do you just have like hydration packs or something?
No, so I mean, it's not so hot. It's still you're about I don't know, 1,000 foot away from the lava surface itself. So I mean, occasionally, if the gases came towards me, I would feel that's a bit warmer than outside. But otherwise, it's minus 30 or so air temperature. So you overheat climbing up to the cone. So we could take snowmobiles up to the foot of a quite steep cone, but we'd have to trudge up the last half a mile up to the edge of the crater, and often carrying automotive batteries and all the equipment. You are getting overheated because you've got this also this sort of cold weather gear on. And yeah, regulating your temperature was not always easy.
Sure. Yeah. And when you're at the top, like what is it like to see? I mean, you're probably one of very few people on Earth who have ever peered down and looked inside of a lava lake. So is it? I'm assuming that has to be just a fascinating experience, like an otherworldly kind of vision to see.
Yeah, no, it's very, very enthralling and mesmerizing, and I mean, I have to take my eyes off it when I'm kind of there professionally, and I'm there to collect some data and setting the equipment up. So I'm almost completely oblivious in a way of what's going on the volcano until everything's up and running. I've got the computer, I've hit record, I'm collecting data, and now I've got time to kind of lean over the edge and look down there, and yeah, it's absolutely. Is absolutely mesmerizing, because what you see with a lava lake is perpetual motion. You see these red hot cracks that fissure the surface, and the lava is welling up into this lake and then spreading sideways and sinking down. And the lava at the surface cools very, very rapidly, so you get this black, dark crust, and then these red hot fissures where the lava is coming up. And that's just moving around all the time. And there are different kinds of lavas. There are some, like the one at Erebus, which is much more sticky, much more viscous. So it's less mobile, and others like Hawaii, Kilauea volcano, where it's extremely fluid. And then you see these beautiful zigzag red, orange, incandescent fissures, and moving all the time, reconfiguring. Sometimes a fire fountain, for example, in Hawaii, you'll get this activity will start playing on the lake surface for half an hour or so. So yeah, it's and you can feel the heat. Certainly in Hawaii, I can really feel the heat on my face when I'm looking at the lava lake there. And you've got a gas mask on sometimes, but you take that off and you're smelling the gas molecules that just came out from the earth. And it's a very, very multi-sensory experience and very, very gripping for sure,
Yeah.
especially at night.
Oh yeah, oh, I'm sure. The documentary has some wild footage. I guess of I forgot their names, but I think it was back in the 70s or 80s, and it was like this old footage of them. They had to be within 500 feet of like this huge lava flow that was just coming out, and it just makes you think like you said, it's like this does not seem like it's on Earth, like it's somewhere, just a breathtaking display of the Earth's power. I'm sure that was pretty wild. So then that was Antarctica. So take us through what for most of us Americans seems to be totally also out of this world in North Korea. I know there's obviously a lot more political risk at stake for people here. I don't know if it's the same in England or not, but how did that opportunity come to be? Because that when I read that you had done research in over there to help them with, I probably am pronouncing the volcano wrong, but the Paektu San volcano. So yeah, how did that come to be? Because that's fascinating to me.
I got invited there through a friend of mine, a journalist, who then worked for the AAAS, American Association for the Advancement of Science. I'd known him in Cambridge when he was based in an office in the city where I live, Old Cambridge, and but he was then in Beijing, reporting out there, and he'd made one or two visits to Pyongyang, covering science stories in North Korea. And he got in touch with me out of the blue back in 2011 and said he'd got wind of some of the geologists and geophysicists in North Korea wanted to reach out to volcano experts in the international community to get some advice on their volcano, which is called Paektusan, as you said. And Rich Stone, his name, Rich said, could you maybe go in a couple of months? And I said, well, yeah, I could do that. And I got in touch with a friend of mine who's a seismologist, and the two of us went out there. I knew a bit about Paektusan because it was responsible for one of the biggest volcanic eruptions of the last 2,000 years. So a little bit had been written about this eruption. That was really that was the sum total of my knowledge. The volcano is right on the border with China, so the frontier goes through the middle of the crater. This eruption was around 1,000 years ago, and it left a big hole in the ground filled by a beautiful lake. And so we went out there. We arrived in Pyongyang, and what I was completely unprepared for is the significance, the symbolism of this volcano to the Korean people. Actually, not just the North Koreans, the South Koreans as well. It's their ancestral mountain. So they've got these ancestral connections with the volcano, with the crater. So what I was completely unprepared for is the symbolism of this volcano. It's the ancestral mountain for the Korean people. They've got a founder myth that's centered on the crater. And for North Koreans, it's the sacred mountain of the revolution, their struggle against Japanese occupation. And you see the iconography of the volcano everywhere in Pyongyang. You see murals of it in the subway. You see the statues of the founder standing in front of a huge mosaic of this beautiful crater. And so that kind of blew me away. I hadn't been anticipating that. And we spent some days up on the volcano, and we were speaking with our colleagues from Pyongyang, the geoscientists, and they said we really want to monitor this volcano better. We want to understand when did this huge eruption happen around 1,000 years ago. There was no historical date on it. We'd like to understand more about where there might be magma beneath the volcano today. And so we went away. We drew up a project proposal, and we got support from the AAAS, from various institutions in the US and in London, support of the Royal Society of London, and other organizations and NGOs, and we were able to build this collaboration that lasts to this day.
Oh wow, awesome. And was your perception of the scientists there like? Did they seem because North Korea in particular? I know there's a lot of I think they call them defectors or people who have like escaped because of like very horrific conditions there. Did it seem like they were studying science for the sake of studying science, or did it seem like they kind of had like an underlying agenda? Or this could very well just be my American bias, I suppose. But that's the one thing that comes to my mind. It's like, well, what are the actual people like? Because I know a lot of them have they live through these horrible conditions, but there are they do live life. They have jobs. They go through life the same way. So I'm just curious, like if you noticed that the quality of the science that they were trying to undertake there was comparable to the level of science that you were trying to conduct on your own fundamentals, if that makes sense.
Yeah, I'd say yes and no. I think yes, insofar as they have a great thirst for knowledge, as scientists do. Anywhere that you find them, they're curious. They want to pull things apart and put them back together to understand them. They want to understand how the Earth works. And they're very well trained in for example, the kind of foundations of geophysics, the mathematical side of it. They're way better than I am on seismology for sure. What they lack is, because they don't go to the international conferences, they by and large, their English is comprehension is not great. They don't get the journals. I mean, I've become a volcanologist by having collaborations around the world. I've done field work on volcanoes in Italy, in the US, in South America, many places, in collaboration with people in institutes. They miss all of that. So it means they're a very long way from the cutting edge of a discipline like volcanology. And especially because volcanology is not just about the science, it's about how do you interface that with risk management, with the communities that might be threatened by volcanic activity. That's an area that they've got very little experience of, and their volcano hasn't really done anything for many centuries. So it's not something that they've had kind of expertise of an active volcano. So there were many communication barriers, language being one of them. But another just very straightforward thing is I can't email our scientific colleagues in Pyongyang. That exchange has to go through various intermediaries. When we were writing a paper, it was quite complicated because we had to send across a manuscript, and sometimes it would have been photographed on a mobile phone with some handwriting on it, and that would come back to us as a JPEG. Things that you take for granted in communications are not straightforward. And I mean, the other thing I would say is, clearly, I had options of what I did in my career. I think in North Korea it's much more rigid. If you study geology, you will it will be designated what position you go into. So it's a very different system, of course.
Sure. Yeah. Yeah. It's a crazy experience. But it's like you said, it's the cultural differences. And speaking of cultural differences, that's something that you touched on in your book, in the Mountains of Fire, and in the documentary, not specific to North Korea, but in general, like the cultural significance of volcanoes. I didn't know that about North Korea. That's actually really interesting. But Also, in terms of just cultures around the world, like what have you, for example, I don't know if many people know, but the word volcano comes from Vulcan, which was the Roman god of fire. That was something I didn't know. I read in the book. But what makes your book very easy to read for me is it kind of interweaves your research experience and your background and how you got involved with all this with like the cultural and the historical impacts of volcanoes. So what is like the common thread among all cultures that you've studied so far, like that, because it seems like there's almost this like godlike appreciation for volcanoes because of their raw power and everything. So yeah, just maybe like touch on that. Like what have you kind of observed in the different areas of the world?
Sure. Whereabouts do you live?
I'm in the U.S. I'm in Charlotte, North Carolina at the moment. Yeah.
So not too near any smoking volcanic craters, but I mean, imagine that imagine that there was one just a mile out, away from your house, and you looked out of the window at night and you saw the glow from the top of the mountain, and sometimes there'd be some acid rain on your garden because of the way the wind was blowing. Uh, I mean that's something that I've learned going to volcanoes around the world and interacting with the communities that live on them. If you've got a volcano on your doorstep, it's not something that you fail to notice. I mean they're awesome, and seeing that glow at night. I mean it would become very. It's unthinkable that you wouldn't build that into your way of seeing the world, your whole cosmology. Could not ignore this volatile neighbor that you've got. And so I think whether you're on the Big Island of Hawaii, whether you're in Naples in Italy next to Vesuvius, or whether you're in Tokyo near Fujisan, I mean people have embedded the volcanoes into their cultures, and there are many stories, many mythologies around volcanoes that sometimes tell us about their past eruptions, maybe even thousands of years ago. These events can be preserved in oral traditions and stories. So I think it's actually no surprise that how richly they've informed the cultures of many peoples around the world, and more than 10% of the world's population lives within let's say spitting distance of a volcano.
It is wild. So I guess of the active volcanoes, you mentioned Vesuvius in Hawaii. Are those like I guess what makes an active volcano different than a dormant volcano? Is it just the presence of lava, or is it yeah, I don't really know actually.
I don't think I do either. It's when do you say a volcano is extinct? How do you know?
Sure.
I mean, we just have a kind of practical working definition in my field. A volcano that's done something in the last 10,000 years or so, we refer to that as an active volcano. It doesn't mean it's erupting right now. So we often use the term active to mean potentially active, could come back to life again. A dormant volcano, I think dormant is a perfectly reasonable word to use to describe a volcano that is sleeping, that is not doing anything at the moment, but that might come back to life in future. I think that's a helpful bit of terminology. The confusion arises because an active volcano that sort of sounds like a volcano is actually doing something that is erupting. Yeah, it's the terminology is a little bit it's more confusing than it needs to be. But basically, if the volcano is fired up and there's magma at the surface, that could be exploding violently and producing ash clouds, or it could be flowing over the ground in a more benign way as lava flows. Then we talk about an eruption.
Sure. Okay. Yeah, because I went to Vesuvius, and is that considered active, or is that a
Yeah,
that's an
so
active?
Vesuvius, the last eruption of Vesuvius was in 1944, and so that's a volcano. We would consider it an active volcano. It's very quiet at the moment, but it's very carefully monitored because it's in a very populous part of Italy. So yeah, that's definitely in the realms of a volcano that we would expect to come back to life again at some point in the future.
Yeah. Yeah, it was really interesting going through all like the ancient artifacts and seeing all the stuff at the site, like the historical site, and kind of going back to what you were saying before about like the living day to day and seeing this like massive volcano and this kind of reverential love for it and fear for it at the same time. Like I imagine that's similar to people in Hawaii now. You know, they very clearly have kind of this spiritual air to them. So it is just really fascinating, and it's interesting to see how it permeates through culture. So that's really all. That's really all I had for now. I like to end this podcast with a definition of adventure because it takes so many forms. And as someone who's a researcher who's forced to go out on these adventures, it's interesting to hear your perspective. So, how do you personally define adventure?
I've never tried to define it. I mean, I guess it's going out there. I mean, for me, adventure is going beyond the ordinary. And for me, adventure has led me to other parts of the world. It's led me to Antarctica. It's led me to North Korea and Hawaii and so on. And I'm kind of semi-nomadic. I like being on the move. I like being in deserts. I like the physical challenge of environments that are a bit harsh for a human being, the extreme cold in Antarctica or the desert heat in the Sahara. And I suppose it's also that with adventure you don't know what's going to happen. You don't know. Sometimes you don't know where you're going to be sleeping tonight because you've just got a tent on your in your backpack, and you're going to stop traveling when you find a suitable place to pitch it. So that for me is my kind of adventure. But there's an adventure as well in I collect data in the field. I collect a lot of data, and I might collect millions of these spectra in the space of a few weeks. Okay, in some ways my adventure's just begun, because now I'm going to spend months, if not some years, number crunching, analyzing those data and trying to figure out what they mean. And that's a kind of adventure in itself. Okay, it's done from right where I'm sitting right now in front of my computer, and some spreadsheets and playing with the math and so on. So I think it's adventure is what's taking you somewhere where you don't know where it's going to lead. Going to the supermarket's not really an adventure, I don't think, but going into the unknown.
Perfect. Dr. Oppenheimer, thank you so much for your time. Really appreciate it. And everyone should go check out his book, Mountains of Fire, The Menace, Meaning, and Magic of Volcanoes. Really appreciate your time. Thank you so much.
No, well, thanks so much for having me on. I tried to get, I said I'd really like to get some Mount St. Helens ash embedded in the cover of the book.
Oh, that'd be great.
But I think it's got some little flecks in there that kind of simulate it.
Yeah.
I thought, it'd be good to have some of the real stuff.
Yeah,
But
yeah.
no, thanks for having me on. It's been a pleasure.
Of course. All right. Thanks, everyone. We'll catch you next time.